Hi, friends. So we're gonna do some energy practice problems today. So let's just jump right in because it's 1 o'clock. And I'm sure people will be trickling in. So the documents, as always, for the problems that I'm going over, along with their scoring guides, are up in EP Classroom on the date for today's live. All right. So in question 1, we have what looks like a rocket being launched straight upwards. Okay, so we have an initial speed v0, which means, hold on, my computer's saying I have bad Wi-Fi. I don't know why it's saying that. I'm sorry if the call quality sucks. So what was I gonna say? So it looks like we have some initial kinetic energy. We might be dealing with some like free fall type problems if there's no rocket boosters or anything like that, like thrusters or anything. So we might be dealing with an acceleration of g. The rocket reaches some maximum height. Okay, so I'm going to write myself a note that b equals 0 at this maximum height, and then it looks like it turns around and reaches the ground. So remember, when we reach that maximum height, we have to stop at the top. Okay, so a student is conducting an experiment. Hopefully the call quality isn't too bad, guys. It keeps telling me that it's bad quality. I don't know why. I'm sorry. So a student is conducting an experiment to study the motion of 2 toy rockets. In the first experiment, we have rocket X of mass mr launched vertically upward with a speed v0 at time t. The rocket continues upward until it reaches some maximum height at t1. As the rocket travels upwards, frictional forces are negligible. So that means our acceleration is going to be that negative 9.8 meters a second squared, negative because that acceleration is downwards. The rocket descends vertically downwards until it reaches the ground at a time t2. The figure above shows the toy rocket at different times. We have a second experiment, which hasn't been conducted yet, where the student launches a rocket of mass mr, and mr is bigger than little mr. So big M is bigger than little m. It's launched vertically upward with the same initial v0 at a time t equals 0 until it reaches its maximum height. Rocket Y then descends. 2 students in the group are making predictions about the motion of the rocket compared to rocket X. So I'm going to go ahead, since I'm presented with 2 different arguments, I'm going to go ahead and start to highlight which ones I think are, or which statements I think are correct. Okay, so student 1 says rocket Y will have a smaller maximum vertical displacement than rocket X. Well, if they're both launched up with the same speed and they experience the same acceleration, then they should both reach the same maximum height. So I don't think that first statement is correct. Okay. Although it's launched upward with the same speed, they are, and has more kinetic energy. It does because it has more mass. So even with the same speed, if we have more mass and the velocity is the same, we're going to have more kinetic energy. Because rocket Y will have a smaller maximum vertical displacement than rocket X, I predict it will take less time for rocket Y to reach the ground. Well, like I was saying before, I think the vertical displacements are the same. So if the vertical displacements are the same, then the times are going to be the same. So the only thing that student 1 says correctly is that Y has more kinetic energy. So student 2 says rocket Y will have the same maximum vertical displacement. I like that, as rocket X. But they don't both have the same kinetic energy because they do not have the same mass. Since both have the same maximum vertical displacement, I predict that they will reach the ground in the same time. That is correct. I like that part. Okay, so student 2 is just incorrect about the kinetic energy. Okay, so unfortunately on the AP exam, you guys won't have this option to underline, which is a shame. So let's see. Part A. For Part A, ignore whether the student's predictions are correct or incorrect. Do not simply repeat the student's arguments in your answer. So in A1, we're asked to figure out which aspects of student 1 reasoning are correct, if any. So I already sort of did this. Sorry for the video going crazy. I'm just flipping my screen around. So student 1 is correct that Y has more kinetic energy. So let's see. So student 1 is correct in saying that Y has more kinetic energy. So that's the part that's correct. Now I have to explain my answer. This is because X and Y have the same velocity, but Y has more mass and kinetic energy is 1/2 mv squared. Okay. So which aspect of students 1 reasoning, if any, are incorrect? Okay. So basically everything else that student 1 says is incorrect. Okay. So what we're going to focus on, or what they're really saying, is rocket Y has a smaller vertical displacement and therefore less time. Okay. So student 1 incorrectly states that rocket Y has less vertical displacement and therefore travels for less time. Okay, so that's what the student says. That is incorrect. Okay, so we have to say something along the lines of both rockets have the same V0 and acceleration, so they will reach the same height in the same amount of time. Okay. So, yes, we could also add in something like the mass does not matter if we wanted to. But I'm actually going to talk about that in student 2. So student 2 is correct in saying that Y has the same max vertical distance and therefore the same max time. Okay. Now there's actually 2 ways we could go about explaining why student 2 is correct. Okay. We could use the conservation of energy idea. Okay. And in this case, we have kinetic energy converting to gravitational potential energy, okay, from launch to max height. So 1/2 mv squared converts to mgh. Now, if you notice, mass cancels on both sides, which says that this maximum height is independent of the mass. Okay. You can also take the kinematics approach, okay, and we can talk about the 2 equations. The timeless equation, which is going to show that if you have the same initial velocity and the same acceleration, you're going to travel the same distance. And similarly with the time, except there's no t or 2. Okay? If you have the same initial velocity, same final, same acceleration, your time is the same. So either way, we kind of have to take this into account, but how you talk about the vertical displacement is up to you. So student 2 is correct that both rockets travel the same max distance. Okay. This is because with the same v0 and acceleration and v final, according to the final squared is v initial squared plus 2AD. The distance, or height in this case, must be the same. Similarly, with v equals v0 plus AT, student 2 is correct that the time is the same. Whew, that was a little bit longer than you would maybe expect. Okay. All right, and then which aspect of student 2's reasoning, if any, is incorrect? So student 2 is incorrect in saying the kinetic energies are the same because mass y is greater than mass x, and kinetic energy is 1/2 mv squared. The kinetic energy of y is going to be greater than the kinetic energy of x. Okay, so unfortunately with these, it does kind of get a little bit redundant when you're doing reasonings for why correct and incorrect for both students. A lot of the times I've seen on these types of AP problems, you'll either just have to pull out what's correct or what's incorrect. Doing both, like our answers to A2 and A3 are essentially the same, just proving opposite. So it's a lot to do both correct or incorrect, but it's a different exam this year, so they might do that. I'm just going to see if there are any questions, and it does not look like there are. Remember, you can ask questions in that Q&A section. Okay, let's continue on with this problem, the rocket problem. Nope. Okay, so use quantitative reasoning, so equations, as needed to derive expressions for the maximum heights achieved by rocket X and rocket Y, and express your answers in terms of V0, MR, MR, G, and any other fundamental constants as appropriate. So again, to find that maximum height, we can either use energy conservation or kinematics. Doesn't matter which one you use. I'm going to use energy conservation because why not? Okay, so as we know, we have kinetic energy being set equal to gravitational potential energy because we're starting with kinetic, and then it's going to convert completely to potential when we get to the top. So we have 1/2 mv squared is mgh, and like I said before, the m's end up canceling. Okay, so in this, we are solving for the maximum height, which is this h value. Okay, so 1/2, the velocity should be expressed in terms of v0. Okay, and then I'm going to divide both sides by g, so there's the equation for my maximum height. Okay, not too bad. Okay, again, you could do this using v final squared is v initial squared plus 2AD. Actually, on your reference table, it's written as v equals v0 plus 2a delta x. These are squareds. Okay, so this final velocity, if we're at the maximum height, would be 0. This would be v0 minus 2g delta x. So I subtract v0 from both sides. So I have negative v0 squared is negative 2g delta x, divide by negative 2g. And I get the same answer that I did before. V0 squared over 2g is my change in displacement. So again, either way works. Okay, so then use quantitative reasoning and including equations to derive expressions for the time it takes rocket X and rocket Y to reach the ground after reaching their respective heights. So again, this height here is for both X and Y. Okay. So we need to figure out the time it takes from this max height to fall back down. So we're essentially finding T down. Right? For this, we do need to use kinematics equations. So right now, the information we have is we have the change in displacement or change in y, which is h. Okay? We have the initial velocity, which is 0. Okay? We have the acceleration, which is negative g, and we're looking for the time. So that tells me that I should probably use the distance versus time equation. Okay, but I'm going to write it with y's instead of x's since we're in the y direction. So y equals y0 plus v0 t plus 1/2 a t squared. So this side, if I was to subtract y0 here, that would really be delta y. So this is h equals v0, 0, 1/2, and we're falling, so that's why it's a negative h, negative g, t squared. Okay. So I multiply both sides by 2 and divide by negative g. So 2h over g is t squared. So t is the square root of 2h over g. Okay. But the thing is the problem does ask us to do two different times because we are based on maximum height hx and hy. So we need a tx is the square root of 2hx over g, ty square root of 2hy over g. You could also say something like h equals hx equals hy and just leave it with one answer. And I think that you would get credit for that. Okay. Now, these last two parts, the equation deriving ones, are probably not going to be on the exam. So if they scare you, that's totally okay. All right, let me go back and look for questions. Oops. Any questions? It does not look like there are. Wonderful. Again, I apologize if there's like bad video quality. Let's continue on. Okay. So then part D is explain how any correct aspects of each student's reasoning identified in part A are expressed by your mathematical relationship in part B. Okay. So in part B, we show that mass does not affect height. Therefore, X and Y have the same max height. Yay! So in part B, that's where we did the mass height. We showed that it's not even taken into account in kinematics, meaning mass is not even taken into account in kinematics, or it cancels using conservation of energy. So if you use kinematics equations, you would say mass isn't even in the equation to find maximum height, or you could say that the mass cancels from the conservation of energy equation. Okay. Then D2 says explain how any correct aspects of the student's reasoning in part A are expressed by your relationship in part C. So in part C, we show that time only depends on G and H, okay? Because remember our equation was T is the square root of 2H over G. If H and G are the same, which they are for rockets X and Y, then the time to fall is the same. Okay, so we're showing that in time C, time only depends on the height. So if the heights are the same, then the times are going to be the same. So D is probably something you should or will see on this year's exam. But instead of you coming up with the equations, you might be presented with the equations and asked how it expresses your or justifies your reasoning. Okay. Last check for questions on this example problem. And again, it doesn't look like there are any. So I'm going to go ahead on to problem 2. Okay. Problem 2. There it is. Okay. So we have this person on a platform who appears to be jumping from said platform attached to a bungee cord. So we are bungee cording. So there's definitely gravitational potential energy up here. Okay, there might be kinetic energy depending upon if this person is moving, and maybe some potential energy because this cord might be an elastic cord that can be modeled as a spring. Okay. All right, let's read the problem. All right, so then we have some second state, it looks like. So an amusement park ride, this is a dangerous amusement park ride. An amusement park ride is designed such that one end of an elastic cord is fixed to a platform that is a distance d above the ground. The other cord is attached to a person of mass m. The cord has an unstretched length of L to begin the ride, so that's its unstretched length. So that's essentially the initial length. To begin the ride, the person jumps up from the platform with an initial speed of v0. So they do begin with both gravitational potential energy and kinetic energy. As the person falls, the elastic cord stretches and can be modeled like a spring. So we are going to have some spring potential energy involved in this problem. So it's looking like some of this gravitational potential energy is going to convert to spring potential energy and some kinetic energy as we fall. And then when we reach the bottom, we will likely just have spring potential energy. Okay. So after the cord can no longer be stretched, the person is a distance h above the ground and is no longer in motion. Okay, so at this height where this person is here, V, oh my goodness, I can't write, V equals 0. The reference for 0 gravitational potential energy of the person, cord, earth system is a distance h. So this is also our h equals 0, which means at this lowest position, we only have spring potential energy. Okay. All frictional forces are negligible. All right, awesome. Okay, so the initial state of the system is shown in figure 1. That was on that first page, which I represented here. It's when the person is in the air, falling, but still at the max height. The cord hasn't been stretched yet. So describe the energy transformations that take place from the initial state to the final state of the system. For each form of energy, identify the object or system that has that form of energy. Okay, so initially, Okay, the person has kinetic energy because that's the thing that's moving. And then the person Earth system has gravitational potential energy. Okay? Remember, in order to have any kind of potential energy, you have to have that second object in your system, whether it's the Earth or the spring. Okay? So this converts to all spring potential energy in the spring spring person cord. Oops. Nope, that's the spring and the cord are the same thing. So let's change this to, why can't I spell cord correctly, guys? So cord, person, Earth system. Okay. So since we were talking about kinetic energy and gravitational potential energy initially, in order to get rid of those, they still have to be in our system because we have to be able to say that those energies are zero. And then in order to have the spring potential energy, we have to include cord, person, or the cord within our system. Okay. So it's a tricky question in the sense that you have to think about all the different types of systems. Okay. Okay. So again, we're converting kinetic energy in the person and the person cord or the person Earth system with gravitational potential energy. And then that converts to spring potential energy. All right. Next, derive an expression for the spring constant of the cord in terms of D, L, H, V0, M, and physical constants as appropriate. So that could be G. All right, so we are going to use conservation of energy to do this. So we're starting off with kinetic energy and gravitational potential energy, and that's all converting to spring potential energy. Okay. So the kinetic energy is probably the easiest equation to fill in here, because remember, kinetic energy is just 1/2 mv squared, but in this case, we're using V0. Gravitational potential energy, okay? The initial gravitational potential energy is mgh, but that height represents the distance vertically from our zero position. So our zero position is the distance h. We are a distance like this above h, which is actually a distance d minus h. So this is going to be d minus h. Okay. Then we have 1/2 k, but remember, x is change in length. Okay, so that's the final length minus the initial length. Well, the initial length is the length L. The final length is the same as the change in height. So this ends up being d minus h minus L. That's not ugly at all, guys. Not at all. Okay. One thing to keep in mind is that we cannot cancel the m's because there's not an m in every single term. We cannot cancel the 1/2 because there's not a 1/2 in every single term. So this equation is just going to be but ugly. All right, so we're going to multiply both sides by 2 to get rid of the 1/2. Okay, so you can leave the 2 outside of the parentheses. Squared plus m g d minus h. Okay, or you can go ahead and distribute the 2, whatever you want to do. All right, so that equals k d minus h minus L squared. So then we're going to divide by everything in this parenthesis here. So I'm going to go ahead and distribute the 2. So I have mv0 squared plus 2mg d minus h all over d minus h minus L squared equals K. And that's the final answer. And if that's not the ugliest equation you've ever seen in your life, then I don't know what is. Okay. Again, this triple subtraction here comes from the fact that the X in the spring potential energy equation is really the change in length. The initial length of the spring was L. According to the diagram, the new length of the spring is this distance here, the cord, which we already said was D minus H. So this total length D minus this little bit here. So that's where that triple subtraction comes from. Right. Checking in for questions. Again, it keeps saying I have bad Wi-Fi. I don't know why. Probably my neighbor's stealing my Wi-Fi. Doesn't look like there's any questions. So let's continue on. I may see this in a second. Okay, so suppose that air resistance cannot be ignored. So we're now talking about some real physics. For the position at which the person has jumped from the platform and the cord reaches its maximum stretch length, how does the stretch length of the cord in the case with air resistance compare to the stretch length in the case where air resistance is ignored? Okay, so thinking about this in terms of springs can be a little bit tricky, right? Like, how does air resistance affect a spring? So let's just talk about it or think about it in terms of like a ball thrown straight upwards. So let's say without air resistance, the ball goes to this height H, okay? Well, we know that air resistance exists, and air resistance is going to go less high because air resistance is essentially friction, and friction can do work on our system, which means we are going to lose energy as the object travels, okay? So similarly to the ball being thrown straight upwards going less high, this cord or spring is going to stretch less far, okay? So sometimes switching around the problem and thinking about it in a different way helps me, okay? So the cord will stretch less far. This is because air resistance does negative work on the person, cord, earth, system, decreasing the total usable energy. This means there will be less energy at the low point than before. That's not how you spell before, but you got it. Before, so this means the cord has stretched less far. Okay. So basically, we're talking about air resistance doing negative work on the system. That takes away energy from the system, so the cord is not able to stretch as far. Okay. And that is actually the end of that problem. So I'm trying to flip back to the live to see if there are any questions. And it does not look like there are. So that's going to bring us to the end of today. It is nice outside today, a little chilly, but definitely good for a nice walk. Have a wonderful rest of your day. I will see you guys soon. Bye.